Namaskaram. In last session, we will see what is a conservative vector field. In this session, we will discuss a simple test for a conservative vector field. These are the solutions of previous homework. Okay, this is the definition of conservative vector field or irrotational vector field. There exists a function phi such that its gradient equal to given vector field f. We say that f is conservative and phi is called its potential function. Okay, this is a very simple test for check whether the given vector field is conservative. A vector field f is equal to, this is in 2D case, a vector field f is equal to fxyi plus gxyj is conservative on some domain D if and only if dou f by dou y is equal to dou g by dou x at all points in that D. Okay, so that means if a vector field satisfies this condition in some domain, then that vector field is conservative in that domain. Okay, so similarly we have a result in three-dimensional space. If f is a three-dimensional 3D vector field, then it is conservative in some domain if and only if it satisfies these three conditions: dou f by dou y equal to dou g by dou x, dou f by dou z is equal to dou h by dou x, and dou g by dou z is equal to dou h by dou y. This is equivalent to curl of equal to 0. Okay, if you compute the curl of, then all the terms are 0, so curl of equal to 0. Okay, so to verify a three-dimensional vector field is conservative, either you have to verify these three conditions, or you take the curl of. If curl of equal to 0, it is conservative, or it's called a rotation. First problem, determine whether the vector field fxy is equal to y plus xi plus y minus xj is conservative on some set. Okay, it is clear that this is our f function, this is our g. So f is equal to y plus x and g is equal to y minus x. So we have to compute fy and gx. Okay, so what is fy? If you differentiate this with respect to y, this becomes 1. And what is gx? That is minus 1. It is clear that fy is never equal to gx for any xy, because fy is always 1. Whatever be the value of xy, fy is always 1 and gx is always minus 1. They are never equal. Okay, so that means this function doesn't satisfy this condition, fx equal to fy equal to gx in any point. Okay, so what is the conclusion? There is no point in the xy plane such that this function satisfies this condition. So this is not a conservative vector field on any set. So this is not a conservative vector field on any set. Okay. Next problem, let fxy equal to 2xy cube I plus 1 plus 3x square y square j. Show that f is conservative on entire xy plane. Okay, and hence find the potential function. So it is clear that here f is equal to 2x y cube and g equal to 1 plus 3x square y square. So you can easily verify the condition. Here fy is equal to 6x y square and similarly gx also 6x y square. So which implies fy equal to gx for every x and y, So this function satisfies this condition on every point in xy plane. So this is a conservative vector field in entire xy plane. Okay. So next you have to find the potential function. Okay. So we know that since it is a conservative, there exists a function phi such that f is equal to del phi. And we have seen an example in previous session how to find this phi. Okay, anyway, here this is our f and del phi is dou phi by dou xi plus dou phi by dou yj in the case of 2D. And comparing these two, that means comparing the coefficient of I and j, we get dou phi by dou x is equal to 2x y cube and dou phi by dou y is equal to 1 plus 3x square y square. Okay, we can evaluate the potential function phi in two ways. Either we integrate this equation or by this equation. Okay, anyway, we consider the first one. Similarly, you can find the phi using the second one. Okay. Okay, so we integrating this equation with respect to x on both sides. What happened? The left side become 5. You integrate this equation with respect to x on both sides. Left side become 5, and what right hand side is this x become x square by 2. You can cancel these two. So this become x square y cube plus a constant of integration. And what is our constant of integration? Because now we integrate with respect to x, so the constant of integration is function of y. Okay, so here we can take our function constant of integration as some k of y. It's a function of y. Because if you differentiate this expression with respect to x, this term becomes 0. That's why we're taking our constant of integration as some k of y. Okay, next we are going to differentiate this expression with respect to y for comparing this with this equation. Okay, so if you differentiate with respect to y, what happened? This become dou phi by dou y. LHS is dou phi by dou y. What is the derivative of this one? This is x square into 3y square. So 3x square y square plus derivative of k of y with respect to y. We can denote it by k dash of y. So here this dash represents derivative of this k with respect to y. Okay, already we have dou phi by dou y. Comparing these two, what happened? Already this term is common. 3x square y square is there. 3x square y square is here. So what about k dash of y? Yes, comparing these two, we get k dash of y is equal to 1. Okay, to find k, okay, to find k of y, we have to integrate this expression, this equation with respect to y. Okay, now this k is a function of y alone. So we can integrate. So what about left hand side? Left hand side become k of y. You integrate this with respect to, because this is derivative with respect to y, and k is a function of y alone. So if you integrate this with respect to y, we get k of y. And what about the integral of 1 dy? Right side become integral of 1 dy. Now we're treating our this expression as a function of y alone. So this become y plus some constant of integration. Okay, now this c is a number because here k is a function of y alone. K doesn't depend x. So the constant of integration is simply a number constant. So by substituting this k of y in this equation, then we get phi. So our phi xy, our potential function phi xy is equal to x square y cube plus y plus c, where c is a constant. Okay, c is a number. X square y cube plus y plus c. Okay, next problem. Let fxy is equal to e raised to yi plus x e raised to yj. First question, show that f is conservative vector field on xy plane, entire xy plane. Okay, it is clear that here f is this one and g is equal to this one. And what is fy and what is gx? Both are equal because here fy is e raised to y itself and gx is e raised to y. So both are equal to e raised to y. Okay, so this is a conservative vector field in every xy in the xy plane. That means this is true for entire xy plane. Okay, next we have to find the work done by the field on the particle that moves from 1 0 to minus 1 0. Okay, here this is our 1 0, this is minus 1 0. So it is moving in this orientation along the semicircular path C shown in figure. They didn't give any equation of this curve. Why? Because here this vector field is conservative. Then we know how to evaluate work done. What is the formula of work done? Yes, work is equal to integral over C f dot dr. Okay, but now it is clear that this f is conservative. So what happened? So since it is conservative, we can find the potential function. Okay, so we can write f as del phi for some phi. Okay, so this equation become integral over C del phi dot dr. Then what is our fundamental theorem? then the fundamental theorem says that this integral is nothing. This is equal to phi at the initial point x naught y naught minus phi at the terminal point x1 y1. In this case, x naught y naught is nothing. It is 1 0, that is starting point, and the x1 y1 is minus 1 0. Okay, because this integration doesn't depend the path since f is conservative. So we are not interested to the path. We are interested only on the starting point and end point. Whatever be the path, this integration is always same. So here our aim is to find this potential function, as similar to the previous problem. Okay. Anyway, anyway, that part is left with you. We can easily find phi, as similar to the previous problem. Anyway, the phi is x e raised to y plus some constant of integration. Okay, so this is our phi. Then you can easily find this work done. So our work done is integral over c f dot dr, that is equal to integral over c del phi dot dr, and we know how to compute this one. This is equal to phi of first point minus second point. So what about that? So here phi of our starting point is 1 0 minus phi of terminal point, that is minus 1 0, that is equal to, what about phi of 1 0? Phi of 1 0 is minus 1 times e raised to 0. Okay, and plus c is a constant, minus, what is phi of minus 1 0? Whenever we substituting this oh sorry, oh there is a mistake actually. This is our endpoint, phi of x1 y1 minus phi of x0 y0. Sorry, this is our endpoint, this is our starting point. Okay, so the corresponding changes, this become minus 1 0, and this is 1 0. Okay, so what is phi of minus 1 0? Yes, phi of minus 1 0 is minus 1 times 0 0 plus constant of integration minus, what is phi of 1 0? Phi of 1 0 is 1 into e raised to 0 plus c. So you can cancel these two constants. So final one is minus 1, it's also minus 1, so minus 2. So this is the total work done. Okay, yes, work done is minus 2. Okay, next problem, show that f is equal to a 3-dimensional vector field, conservative. Find the work done by the field on a particle that moves from this point to this point. They didn't give the path of this curve, path of this particle. Why? Because this function is conservative. Okay, so how to show that this one is conservative? This is the condition. Okay, this one is a condition. Dou f by dou y is equal to dou g by dou x, and dou f by dou z is equal to dou h by dou x, and dou g by dou z is equal to dou h by dou y. Or we can find the curl of. Okay, anyway, this is our f, g, h. This is also, you can easily verify that it satisfies all the criteria. So this is a conservative vector. Okay, you can easily verify this condition. So our aim is to find the work done. We know that the work done is nothing, integral over c f dot dr. Okay, so as similar to the 2-dimensional case, that means the fundamental theorem. In the case of okay, since it is conservative, we can find a phi such that del phi equal to, we can find del phi equal to, there is a phi such that del phi equal to f. Okay, then the fundamental theorem says that that result is true for 3D case. That means this is equal to integral over c del phi dot dr, and that is equal to phi of the initial point, sorry, the end point, the terminal point, that is x1 y1 z1 minus phi of the initial point, starting point, x0 y0. Okay, so this result is true for 3D case, as similar to the 2D case. Okay, so our aim is to find this phi. Then how to find phi? Okay, so this is our condition, f is equal to del phi. So this is our f. So f is equal to del phi. What is del phi in 3D? 3D is dou phi by dou xi plus dou phi by dou yj plus dou phi by dou zk. And comparing the coefficients of I, j, k, we get dou phi by dou x is equal to 2xy plus zq. Oh, sorry, this is zq, not z. And dou phi by dou y is equal to x square, and dou phi by dou z is equal to 3x z square. Okay, then first we have to integrate this expression with respect to x. Then what happened? Left hand side become 5, that is equal to, you integrate this with respect to x, this become x square by 2. You can cancel these two, so x square y. So x square y plus, what about the integral of z cube? Because z cube is a constant with respect to x. So this become x z cube plus a constant of integration. What is the constant of integration? Yes, in this case, the constant of integration is a function of y and z, because now we integrate this expression with respect to x. So constant of integration is a some function of y and z. Because if you differentiate this expression with respect to x, what happened? Dou phi by dou x is equal to like this, and this term becomes 0. Okay. Similarly, you can integrate this with respect to y. Then what happened? The second expression gives phi is equal to x square y, because x square is a constant, plus some function of x and z. Yes. Then what about the last one? If you integrate this expression with respect to z, we get phi is equal to, this term become z cube by 3, and you can cancel these 3. So x z cube uh, plus some function of xy. So now we have 3 expressions for same phi. Then how to extract phi from these 3 conditions? That means phi should satisfy these 3 conditions. Okay, then what is the value of phi? So combining these 3, what about phi? So phi should be, this x square y is common. So suppose you consider second one. The second one says phi is of the form x square y plus some function of xz. So this term is allowed. You got it. In third expression gives phi is of the form xz cube plus some function of xy. So this is allowed. You got it. So these two terms are allowed. So phi is equal to x square y plus x z cube plus a constant satisfying all the condition. That constant should be function of y z, and that constant should be function of x z. That constant should be function of x y. That is possible only when the constant is a number. So C. So this is the potential function. C is an arbitrary number. You can choose any number, no problem. So this is the potential function corresponding to this conservative vector. Now you can easily find this work done using this formula. You simply substitute our end value. What is end value? End value is 314. So we have to compute phi of, so we have to compute phi of 314 minus phi of 1 minus 2. Okay, you plug in these two values in this phi, we get 202. Okay, that's the idea. This is equal to 202. You can easily verify these steps. Okay, these are the homeworks for this session. Thank you.